The first type of series I want to look at is a geometric series. The nice thing about geometric series is that we're going to be able to find the formula for the partial sums, which is going to allow us to not only determine whether that thing converges or diverges, but what it adds up to, which is something we're not always going to be able to figure out for other series. So this is what we call a geometric series. If you look at the form of it, it looks like an exponential, right? You've got a fixed base and a variable exponent. So in the world of functions, this would have been called an exponential, assuming that base was positive. But in the world of sequences, we know that the bases can be negative and they're still okay because you're only taking it to natural numbers. So r could be a positive or negative number. The terms look like this, right? Notice all that's happening is the power on r is going up by 1 each time. So each term, if you look at it written out, you start with some value, a. So a is always your first term. And notice to go from each term to the next, you multiply by r, right? Times r, times r. R is called the common ratio. The reason we call it the common ratio is that if you look at these terms in a ratio, if you take the second term over the first, or the third term over the second, or the fourth term over the third, every one of those has the same ratio. So either way, think of it as the thing that you multiply by each time or the ratio that you get of taking each term over the previous. All right. So what I want to look at is under what conditions does this series converge and under what conditions does it diverge. So I want to try and figure out a formula for the partial sums, because remember, that's really the definition of convergence and divergence is based on the partial sums. And the nice thing about geometrics is I can find that formula somewhat easily. So let's write out what is the kth partial sum. So if you add up the first k terms here, you get a plus ar squared all the way up to, now let's think about what that last degree is going to be. The degree is always 1 less, right? The first term has degree 0, second has degree 1, third has degree 2. So the kth term actually is 1 degree less, right? Okay. Now the goal here is to get rid of the dot, dot, dot. The problem is right now all this formula says is add them all up. But could we write it without the dot, dot, dot in some what we call closed form? And we can. And the trick is just a little algebra trick. Let's multiply through by r. When I take that first term times r, I'll get a times r, which I'm going to line up with that one. ar times r is ar squared. And really what we're going to do is raise the power of each one of those by 1. So this one, that last one becomes ar to the k. Now, the clever thing to do is subtract that first one, subtract the second one from the first. So we have s sub k minus r s sub k. And notice what happens here. Cancels, 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 cancels. Everything cancels except for a minus ark. We got rid of the dot, dot, dot. But I'd like this to just be the partial sum formula, or the partial sum. So let's factor out that S sub k. And just for neatness here, I'm going to factor out that A. And now divide. And we've done it. The partial sum formula for a geometric is simply that. So if you wanted to know the sum of the first 1,000 terms, you don't have to add them up. You just take the first term times 1 minus the common ratio to the 1,000th power, 1 minus the common ratio. Now the question is, what if you want to add all of them up to infinity? So that's what we define to be the limit of this. So this is the rare thing that you could actually find this formula. Geometrics you can, but in general for just any old series, it's not typically doable to get that closed form formula there. Okay, so what happens is you take the limit as k goes to infinity. Of those partial sums. Well, most of this has nothing to do with k, right? Only that one little term does. So I'm going to use our limit properties. A over 1 minus r is a constant. Then I have 1 minus the limit as k goes to infinity of r to the k. R is a fixed number, right? It's whatever our common ratio is in our series. Well, think back to Theorem 5. When is that going to converge? When the absolute value of r is less than 1. So we know that this equals a over 1 minus r times 1 minus 0, provided that that is less than 1 in absolute value. That's what Theorem 5 said. So I'll say by Theorem 5, provided the absolute value of r is less than 1. Right? If that base is less than 1 in absolute value, taking higher and higher powers is going to bring it down to 0. And there we have it, a over 1 minus r, so long as the absolute value of r is less than 1. So what do we know? Given any geometric series, all you have to do is look at the r. If the r is less than 1 in absolute value, that series converges, and more specifically, it converges to a over 1 minus r. If r is not less than 1 in absolute value, this series diverges, because this little term here, this limit doesn't exist, and so the limit of the partial sums does not exist. So we got 2 for 1 out of that. Now we know when a geometric converges. It converges when absolute value of r is less than 1, and we know what it adds up to, a over 1 minus r. So next time we'll look at a concrete example of a geometric series and using this fact here to determine whether the series converges or diverges.